In this video, we're going to use a table of values and Simpson's rule to approximate the value of an integral. So we've got a table of function values for a function g, and we're asked to use Simpson's rule to approximate the integral from 0 to 1.6 of g of x dx. And we're also asked to estimate what the error might be in this approximation if we know that the fourth derivative is in between -5 and 2 for all x that's in the interval that we're integrating over. All right, so for Simpson's rule again, we need to plug in or figure out what the function value is at each of the subintervals. Remember, the ones in the middle get multiplied by alternating 4s and 2s. And then the last ones are just the function values, not multiplied by anything other than 1. The multiplier out in front is delta x over 3. So how are we getting delta x? Well, again, we're trying to use as much of the data as we can. We'd love to be able to use each of the data points. To be able to do that, the change in x over from one x value to the next is 0.2. So we'll use 0.2 for our delta x. Our function values, of course, are the corresponding values of the function at those points. The other thing that we need to worry about for Simpson's rule is to make sure we have an even number of subintervals. So our first subinterval goes from 0.0 to 0.2. That's the first subinterval. The next one from 0.2 to 0.4 is the second subinterval, and so on. So we see that we have 8 subintervals in this case. We have 9 function values, but we'll get 8 subintervals. So we're good as far as number of subintervals to be able to use Simpson's rule. So plugging it into our Simpson's rule formula here and using a calculator to give us an approximation, we get about 19.2. Finally, we're being asked to estimate the error in Simpson's rule. Well, we have the formula for figuring out an upper bound on how big the error can be in absolute value. So remember that to be able to do that, we need to know what the absolute value can get of the fourth derivative of the function. And that's why we're given information about the fourth derivative, whether it's always in between. But remember, we need to know what's the biggest it can get in absolute value. Well, notice that the biggest absolute value we can possibly get from the fourth derivative in this case is 5. We don't want to use the 2 because in absolute value, 5 will be bigger. All right, so then we'll use our error formula for the Simpson's rule. 5 is the biggest the fourth derivative can get. The length of the interval is 1.6. We raise that to the 5th power. Divide by 180 times the number of subintervals raised to the 4th power. Simplify that, and we get that the absolute error in using Simpson's rule to approximate this integral is bounded above by 0.00007.